Hello and welcome to Explaining Rust Analyzer, a video series where we try to understand how Rust Analyzer works under the hood, one subsystem at a time. So, last time we looked at the implementation of immutable green trees in their own syntax-free library. And while doing that, we've noticed that there is a suboptimality in the implementation of cache for green node builder. So I think it might be a good opportunity for us to go on an adventure and just to try fix this issue. So in this video, I won't actually be trying to explain things. I will just try to record myself investigation and fixing a particular issue just to give you a feeling of how to work with Rustalizer. Okay. So let's go to the Rerun and take a look at the problem again. So we have this builder thing, and inside of it we have this caching. And the idea is that they are basically internal trees. We want to make sure that each distinct green tree is stored only once. And for that, we need to compare a new tree to a tree we already have. And for that, we need to hash and compare the trees. And we've noticed that if you just naively hash the tree, that would be slow. Because if you say you try to put a tree 5 level deep in the cache, then you need to hash like every child and every descendant on the tree. And that actually, I think, would mean that you would do like n squared of operations or something like that. So we want to avoid that. And instead of recomputing hashes from scratch, we just pass in the already computed hashes of children. And while we do this optimization for hashing, we actually don't do this optimization for equality comparison. When we try to answer a question if this node is in the cache, it would be enough to just compare children using pointer equality. But here we do it using like the standard equality, which recursively walks both the trees, which is slow. So we're going to fix it. And before we start doing that, I realized that I didn't actually mention this awesome link. So a lot of optimizations in Rowan are copied from Roslyn, and they aren't actually really greatly documented in the official documentation. So here is on like someone's random GitHub on a like wiki. There is a document which contains like badly copy-pasted discussions in some kind of Roslyn internal forum, which is long that. Basically, that's kind of like really not well published source information, but it contains a bunch of tips. So if you would like to notice how to like make this immutable trees production ready, then please do check out this like nice not a blog post. Okay, so basically what we want to do here is to check this to replace this equality by kind of like value with equality by syntax and checking if it works. Let's start with going to Rust Analyzer directory and just building and testing stuff to make sure that everything works correctly. It's interesting. Why are we downloading new crates? Looks like some cargo update landed in the meantime. So yeah, that's kind of like when I work on Rust Analyzer, the first thing I do is update the repo and like rebuild and run tests to make sure that the baseline actually is reasonable. Let's wait a couple of seconds for it. Okay, so everything works fine. The next thing we will do is that we will replace the Rerun library from create.io with the one from the local folder. And I wonder if it makes sense to move Rerun repository into Rust Analyzer. That would make some things easier, probably. Okay, so we go to the target.toml and uncomment patch section. So it's a frequent use case that we want to change some bigger external dependencies in Rust Analyzer, and that's why we have these patch statements prepared so that you can just uncomment it. I personally never remember like the actual syntax with like patch creates.io and like single quotes, so just having it there helps. Let's rerun tests, and yeah, let's note how we actually compile the correct row one. And while it is compiling, let's actually try to find some benchmark. The way to find a relevant benchmark is just to type benchmark into workspace symbols dialog. And here we see that we have like this benchmark parser. And notice that this is a test and not a real benchmark. That's because yeah, we don't actually like run cargo bench, and we do want our benchmarks to at least compile when you run cargo test. And like practically speaking, there's like little difference between running like actual test and running benchmarks. So okay, it seems to work, and let's run this benchmark. So we use copy run command line to copy the command line invocation here. Then we paste it in the shell, and we pass dash dash release, and we also need to actually let me just export this environment variable run slow benches so that the benchmark is actually run. So wait, no, we want this to be a release one. Yeah, better. Yeah, so this is a test. So it is run on every cargo test. However, it is somewhat slow to run, and we don't want actually to spend our CI times running benchmarks. So that's why we by default we skip this use and run slow test. This doesn't make sense to me. I think we had a separate issue for benchmark. Okay, yeah, let's actually fix this while we are at it. Because this isn't actually a test, this is a benchmark. And yeah, I guess it would be all right to commit only this. Okay, and let's create a new branch and submit a pull request, and auto approve it to let Bors check if the tests are passing. Okay, so you see that we ignored this benchmark. Now that we've actually changed the code. Okay, so we see that submitting pull request without actually even compiling code did. Oh god, I even had like training white space there. Yeah, never submit pull request without like building the code. So let's just do this again. Okay, it seems working, so we can reapprove it. Okay, so That's our baseline. Actually, I don't like that those are not aligned. Okay, yeah. Now that makes more sense. So we spent 22 milliseconds parsing and 2 milliseconds traversing the tree. If you're curious, what's this like glorious old parser is? Well, that's this thing. This is a Rust parser from Rust-C, from the time where this parser was a single file, and I believe that was the biggest handwritten Rust file in existence. And actually, I'm actually not sure if that's true. So if you know of a non-generated Rust file which is like larger than 9K lines of code, then please tell me. Yeah, but at that time, it definitely was kind of like the biggest Rust in a single file you're gonna find. Actually, I'm curious, like, so, how long is our parser? Yeah, our parser is like 5K lines, which is actually bigger than I would have expected. Yeah, I guess writing parsers isn't that easy. Although, yeah, it doesn't include like generated syntax tree, so it's like yeah, parser Rust is like indeed like many thousands lines of code. Anyway, we have this like unit benchmark for parsers. Let's now also do this thing. So there is xtask bb, where bb stands for build benchmarks. Let's say that this is our baseline, and that will take some time to compile. And while it is compiling, let's think what we want to do here. Yeah, I guess what we want to do here is that basically we want to change this node token to how this works actually. So children is a green element. A green element is green node, green token. And green node is a thin arc. So I want to, yeah, I guess I want to get a raw pointer to green node data or green token data and compare those. And the idea here would be to actually map both iterators to pointers and then compare those for quality. Yeah, anyway, so the baseline is built. That means that we can do now Rust Analyzer baseline analysis stats. And that should run like the whole type inference and diagnostics and stuff to get some data out of it. And why it is so slow? That's interesting. So recently I've noticed that like this database loading like can take like a dozen of seconds, which is like very strange. I think that is because cargo is being run at that point, but it would be nice to debug that. it seems like overly wide names make our handwritten progress bar not clear the stuff. Anyway, yeah, that's kind of like baseline, but the good thing is that we don't need to remember these numbers because we will then recompile with the modification and check if that's actually faster. Okay, so what we want here is I wonder where. Yeah, let's return here and say an element ID which takes what's that thing? So it's children. So it's real element ref. So we take this thing and we don't need a lifetime here. Always miss a case. And what we want here is something where we only care about pointer identity. Green node data, green token data. Okay, and that's just actually I think we can those are pointers, so we don't need like these two things. We can just use opaque pointers here. Okay, so like this, and like this, and then I think we can map element identity here and element identity here, and presumably that should compile. No, it doesn't. I'm horrible with keys as usual. Okay. So we've changed something. Let's now see if the tests pass. That's like the first thing when you optimize something. You need to make sure that you didn't actually broke the stuff, because it's like the easiest way to make things fast is to make it immediately return the wrong answer. But that's not interesting. We want to make stuff fast while also computing the right answer. Yeah, it is slow and it might be surprising. And you might even think that we broke something and like the thing has stuck. But that is because we actually have this run slow benchmarks variable set. So like the code is slow because we're trying to run a benchmark in a debug mode. If we do this in separate tab, which doesn't have this any variable set, then we see that it has to work. Okay, so check. Okay, and let's run this with counts enabled, just to make sure that our caching strategy, that we didn't like broke the cache, because again, we are fixing a cache. And the problem there is that correctness errors do not actually manifest themselves as test failures, because the observed behavior remains the same. It's only performance that differs. Luckily, uh, we have these additional counts, which allows us to check how many things are there and see if they are the same or not. Yeah, that's horrible. I need to check this. Anyway, it might be hard to read. That's interesting. So in the fast equality check, the amount of live tokens is actually bigger. That's exactly the thing which shouldn't be happening. So I wonder if stuff is actually broken. Let's then rerun this just to make sure that those numbers are actually deterministic, which is something I'm not sure about. I think they should be deterministic, and if they aren't, that would be a bug, but who knows. Yeah, especially interesting is that I think we saw the difference in the tokens, while actually it's only the caching strategy for nodes which we are changing, which doesn't make a lot of sense to me. Okay, these are exactly the same. So let's do with fast equality check. And while we are running this, let's just look here and see if maybe we can quickly spot a bug, but this does seem reasonable to me. Not sure what's going on. Yeah, sadly, when you enable counts, the stuff is excruciatingly slow. Okay, yeah. I guess that that makes a little bit more sense. No, it doesn't. So we have more life tokens, and we have more live nodes as well. Mm-hmm. I wonder what we should do. Yeah, just to like quickly get a read on performance. let's run the benchmark a couple of times. To make this reproducible. Well, then let's go back to Rerun, stash our changes, and run benchmarks a couple of times more. Okay, so this is without changes. And this is with changes. Yeah, it seems like it did make stuff like a little bit faster. Yeah, but somehow this changed the result. That's interesting. Okay, let's now rerun the benchmarks. Without array counts to get a read on the overall like runtime performance, if it's different or not. And while we are doing that, let's take a closer look at what is different here. So yeah, I think that should be all right, because yeah, it's like I was thinking that like maybe with like this casting of pointers we confused like pointer to a pointer with a pointer, but that doesn't seem to be the case. It looks like it does the right thing, because that is the actual data. It's not a pointer, so this is like one pointer, and we take this one pointer and cast it. Okay, have I forgot the queue? Yep, I forgot to pass the quiet here. What's this child ref? That's yeah, but all seems broadly correct to me. Okay, let's look at the numbers. And yeah, notice that what we are printing here is like wall clock time, as well as like the number of instructions executed reported by perf. And how this could, how like this, the first one could be so much faster. It doesn't make sense to me. Yeah, so yeah, I don't understand how we can observe such a big difference in reported instructions between runs of identical code that should be the same. Okay, doesn't make sense. Let's repeat it a couple of times. I kind of like looking at like these two entries, it's like pretty clear that this actually did make stuff faster. But at the same time, like this one doesn't look like significantly faster. And yet like the difference between these two is big. So it's something really, really strange going on. Or I'm just like misunderstanding stuff. And yeah, sadly, like kind of like for this kind of optimization work, a lot of time is spent actually like waiting for the benchmarks to complete. I guess we should switch like right now the problem is that I'm using Rust Analyzer itself as a target for the benchmarks. And the problem with that is that it's like too big to quickly finish any particular run of a benchmark. Yeah, okay. The stuff on the right does seem to be substantially faster than the stuff on the left. That's great. But it apparently is less efficient in terms of actual caching. So let's do. Let's also pass memory usage and see if that makes a big difference. Yeah, and we really need to make this faster or come up with some better benchmarking target to not waste time just waiting on the benchmarks. Okay, and now faster quality check. Yeah, notice that when I'm passing memory usage flag, then I get this extra memory usage. Yeah, so yeah, that's kind of concerning. It does seem like it becomes faster. but somehow less memory efficient. Okay, let's rerun our test with array count. And I think to make array count work, I need to enable it somehow. Count me enable. This is what I need to call. Like in count me, there is like this sum. Okay. Enable true. Count me. A file count me. Так. Get all, and I want to print them, and I want to print them using display. Hope it works. Okay, right. I really hate this like very long row utility types. Let's fix that while we are at it. This should be in the cursor. Count syntax element. It prints the whole name here, so if I just define syntax element here, I should actually get a more reasonable count. Okay, that's better. And now let's go to the cache. And if we revert those changes and we run benchmarks, so there's only difference in the live counts. Max life for token is the same, max life for green nodes changes, and in a version where that's strange. Okay, so let's just print a count of hits again. Hit. Let's actually do this. Let's commit this enabled implementation under some commit so that we don't lose it. Committed the wrong thing. I hate when I lose changes. Okay, so this is what we wanted to commit. And let's see how many hits it gives us. So 57 and something hits. Now if we... Let's do this. Yeah, I don't have like a very great workflow for how to actually like check several things at the same time. Okay, so maybe... No, it doesn't make sense. I don't understand why changes why this. What's going on here? Yeah, so apparently we are getting exactly the same number of hits when parsing specific code, but we also get the different consistently different number of green nodes in total. At this point, I'm just like randomly recompile stuff. Doesn't make any sense to me. Why are we creating more green nodes? Okay, because, okay, hit is actually not here, hit is actually here. And by the way, like notice how like this count me thing is like helpful for quickly debugging issues because I can just like print the out without any settings. Okay, so yeah, okay. Now we have a difference here. So this version is the old one, and it gets 2000 hit more. Okay, it makes sense. What doesn't make sense is why. So, is my initial assumption correct? In that pointer quality doesn't actually equivalent to an actual quality here. Okay, so let's just like brute force it. I want to say okay, so we found the bug interesting. That's value. Yep. Basically, what you want to say is that if so, this is value ec, and this is that. We want to say that if they are equal, let's make a sanity check. If they are equal by pointer, then they surely should be equal by value. And that works. So now let's try to flip this around. Okay, this fails. Now let's just like print everything. Okay, so they are different in a single token. Let's now manually check if their addresses are the same. And the addresses are different. And I don't know, but to me this sounds like a bug. Because why would they be different? I wonder if this has to do with, are we calling, so there's a method which creates this token cache with predefined cache. I wonder if they are using this. No, we aren't using this. It's just like the raw cache. Then why? Could it be that like this is completely broken and the actual hash functions are different? So let's actually derive hash function. Oh, wait. What is tokens? Tokens is a hash map using fx hasher, so that should be correct. Mm-hmm. So this is getting somewhere. It seems like just our like manually compute the hash logic was busted. Oh wow. I wonder if the same's true for nodes. Yeah, that's getting way more curious. You see how I kind of like rise up from my tomb. That's interesting. Okay, let's do the same thing for nodes. Mm-hmm. Yes, it's how did this even work in the first place? That's very wrong. Can I? Yeah, so it seems like the problem is that we are just using two hash functions in this hash and in the actual hash table, because derived hash doesn't match whatever hash we occupy. Okay, yeah, let's first fix it and then debug it. It's always it's always like the right approach to things. Like you can always debug later, but you need to fix this immediately. Okay, and we want to hash this. So if it turns out that like this is like that this was completely busted before that, let's so I really want to hash this to state. And this one I also insisted on. Shit, that doesn't make sense. How do we like compute this? The hash. Oh, wait. So we hash the hash of a child. So that's not what I have written. So that means that I need to can actually like, get hasher out of it. Like, can I create a new hasher? Apparently I can, so that's definitely not the right way to do this. And then I want to finish. Okay, so this seems like what we want to have actually. Okay, it's getting annoying. Let's see if we okay, I've recently added the feature to Rust Analyzer where it like panics in development mode, and it seems like we have too many panics and we need to fix them all. Okay, self. And we want to hash that. And similarly here, this is actually for green not data. Okay. Okay, tape checks now. And it still fails that assertion. Okay, so did I do something wrong here? So we hash of every child. All right, because right. How it how did this even compiled? Oh, yeah. State hash. No, yes, correct. We want to finish this and we want to hash this into state. Now we are getting somewhere. Okay, so this now is the correct implementation of hashing. And now let's see. Now let's see if this actually works. Like what counts do we get? Uh, what counts do we get if we actually like use the hashed implementation, which is not buggy? So what was happening here is that to implement this caching, we use hash brown hash maps in a very raw way, where we like manually specify hashes. And I thought that we specified hashes every time ourselves, but apparently there were cases where like the default hash functions was used sometimes, and sometimes our hash function was used, and that's not correct. So let's look here. Then correct hash, and then okay, and obviously I want to do this with counts. That's a very exciting moment. We are waiting for the results. And I think what we should see here is that the correct hash version should give us better results overall. In terms of error counts. And that's actually like exactly what I was telling you at the start. That like the problem with caches is that if your cache implementation is buggy, then all your tests are working uh, because there is like nothing wrong, but they're just slow. Okay, so correct hash. And it created like 9 million and like something something. So green node 9,700,000. And here we see 11 million, and here we see 11 million. Wait, is this? Oh yeah, that corresponds to those hits. In green token we have like 5 million. And here we have 3 million. That's exciting. So let's actually I want to compare the speed as well. So let's use correct hash. Actually, let's do this 3 times. You already see that we seem to use fewer memory, which is welcome. But also somehow we're using more instructions, which doesn't make sense. Or maybe it's simply because we are getting more cache hits and checking cache hits actually is more complicated. Okay, we definitely shaved a non-trivial amount of memory. I don't understand why these numbers are so volatile. They should be the same. Okay, I must say that I'm kind of like a little bit tired at the moment, so I don't feel I will do a great job wrapping this up and packaging up as a pull request while also recording it. What I feel great here is that we did debug this issue. We did found an actual bug in our caching implementation, and we fixed it, which is really cool. So I guess it's time to wrap up this particular adventure, and I hope to send an actual pull request later today. Thank you for watching.